Hello friends, as we all know that overall equipment effectiveness OE is critical metrics in the manufacturing industry used to measure the efficiency and productivity of equipment. From an industry perspective, OE is key performance indicator that provides actionable insights to identify and reduce losses in manufacturing operations. Here is a deep dive into OE numerical example from the industry point of view. So let's start. OE overall equipment effectiveness is way to measure how well a machine or a production process is working compared to its full potential. It shows how much of the time the equipment is actually being used effectively to produce good products. Think of it like this: if a machine is available to runs at the right speed, and makes perfect products, it gets a high OE score. If it has downtime, runs slower than it should, or makes defective products, the OE score drops. In simple terms, OE tells how much value you are getting out of your equipment compared to what's possible. It's calculated by combining three factors. First, availability. Is the machine running when it's supposed to? It reflects downtime. Second, performance. Is the machine running as fast as it can? It evaluates speed losses. Third, quality. Are the products made without defects? It assesses defect rates. It is calculated as the product of three components: availability, performance, and quality. Well, objective of OE are as follows. The objective of OE in the industry is to ensure that every piece of equipment is used effectively to deliver maximum value while minimizing waste, inefficiencies, and costs. It acts as a diagnostic tool and a performance benchmark to drive operational excellence and long-term sustainability. Main objective of OE are as follows: maximize equipment utilization, identify and eliminate losses, improve overall productivity, support continuous improvement initiatives, increase profitability, enhance competitiveness, facilitate digital transformation, improve employee engagement, and ensure customer satisfaction. There are certain guidelines for evaluation of OE or calculating OE and its improvement. Let's see one by one. The first slide speaks about the data collection. Important point to note here is that the OE is time consuming and rigorous activity. Hence, most priorities or critical production processes or bottleneck operations to be chosen to work upon for improvement so as to get higher benefits with optimal use of resources rather than consuming resources to less prioritized work. First step: data collection. Gathering historical data on equipment availability, performance, and quality. Identify major downtime causes, speed losses, and defect trends. Steps in OE data collection. First one is define matrix, clearly identify the specific data points required for availability, performance, and quality calculations. Example: line downtime, breaks, stop losses, speed losses, rejection reworks, available production time, net operating time, idle cycle time, etc. Second, choose data source. Identify where and how data will be collected. Example: operator logs, sensors, production reports, etc. Third, implement tools and systems, that is, use of tools like Andon, PLC, SCADA, MES platforms to automate data collection and integrate it with ARP system for seamless reporting. Fourth, train operators and staffs. Ensure all personnel understand the importance of accurate data collection and how to use the OE. how to use the tools for the OE calculation. Fifth, verify data accuracy. Regularly audit data to ensure it reflects actual operations. Let's discuss about the second guideline, root cause analysis. Steps in conducting root cause analysis for OE are: generally, we use tools like Pareto charts and fishbone diagrams to analyze primary issues. For that purpose, we focus on downtime, performance bottlenecks, and quality defects. The guideline steps are: first, define the problem. Identify the specific loss affecting OE. Example, frequent machine breakdowns, slow cycles, or high defect rates. Use OE data to pinpoint which component, that is availability, performance, or quality, is underperforming. Second, collect data. Gather detailed information about the issue such as frequency and duration of downtime, speed variations or slowdowns, types and causes of defect. Use automated systems, operator logs, and maintenance records for accuracy. Third one is analyze the loss. Breakdown of the OE loss into its components to isolate the problem. Availability loss, unplanned downtime, breakdown and changeovers, performance loss, as we know, slow cycles, minor stops or suboptimal speeds, quality loss, defective products or reworks. 4. Use root cause analysis techniques. Apply systematic methods to uncover root causes. Why analysis? Ask why repeatedly to drill down to the root cause. Fishbone diagram, Ishikawa, categorize possible causes into groups like people, machines, method, material, and environment. Pareto analysis focus on the most significant issues contributing to losses. 80-20 rules. Failure mode and effect analysis, FMEA, assess potential failure points in equipment or processes. Fifth one is validate the root cause. Test or verify hypothesis to confirm that the true root cause. Use data and evidence to avoid addressing symptoms rather than causes. Third guideline is set improvement goal. Define specific measurable objectives for each OE component. Example, reduce downtime by 10%, improve cycle time by 5%. An engineer can develop a solution according to the goals. Identify and implement corrective actions to eliminate the root cause. Consider that Considering that the problem analysis is done and root causes are identified, hence actions can be taken as per the specific goal oblique requirement. Solutions may include solutions against downtime losses, optimized preventive maintenance schedules of frequently worn out parts, availability of critical spare parts during corrective actions on sudden breakdown, optimization in time required for maintenance when breakdown happens, and modular fixture design to reduce setup time changeovers. Solution against performance losses are automated feeding mechanisms like install robotic feeders to ensure consistent material flow, use vacuum or conveyor based system for precise material delivery, deploy programmable logic PLC for adaptive feeding based on production speed. Second is material tracking system like implement RFID tags to track material availability in real time, use warehouse management systems integrated with production lines, employ IoT enabled sensors to monitor stock levels and trigger replenishments. Solution against quality losses. Early defect detection using sensors like deploy vision-based inspection system to identify surface defects, use ultrasonic sensors for detecting internal flaws in material, implement vibration analysis sensors to predict mechanical failure before they occur, integrate thermal imaging sensors to identify overheating issues in real time, enhance training on quality standards, etc. Finally, the process needs to be monitored and sustained. Hence, fourth, monitor and adjust is one of the guidelines that emphasize on track the impact of changes using existing data collection method or real-time OE dashboards, refine strategies based on observed results, and fifth one is sustain and scale. This guideline emphasizes on standardized successful practices across all lines or facilities, foster a culture of continuous improvement to enhance the productivity and performance of the employee and thereby company. Let's see a numerical example of OE. Current scenario is as follows. Initial OE data is availability 87.5%, performance 88.6%, quality 93.5%, and then overall OE equipment is 72.5%. And major issues identified are high downtime, machine breakdown, high setup time, material unavailability, performance loss due to misfeed and material shortages, quality losses caused by the late defect detection, downtime analysis. An engineer conducted operational research and observed following planned downtime losses. Breakdown of planned downtime are maintenance 30 minutes per day average, setup and changeover 10 minutes per day, material availability 20 minutes per day. In view to increase the availability time, engineer has decided some actions. Proposed actions are optimize preventive maintenance schedules of frequently worn out parts, availability of critical spare part during corrective actions, necessary material availability during maintenance, optimization in time required for maintenance when breakdown happens, and modular fixture design to reduce setup time, changeover times, etc. Performance loss analysis. Performance loss was recorded as 48 minutes. An engineer also identified following major performance losses. Major contributors of performance losses are misfeed, material unavailability, slow speed. He proposed some actions to enhance the performance of the equipment. Proposed actions are use automated feeding mechanisms to reduce misfeeds to address the issue related to misfeeding, implement real-time material tracking system to address the issue related to material unavailability. For slow speeds, optimize the human interactions with the material and modify the workbenches to enhance ergonomic and rearrangement of the workload of labors. Quality improvement strategies. An engineer identified one critical quality issue, that is late detection of defects leads to rework and scrap. Quality losses was recorded in lost production hours as 24 minutes. He has chosen mitigation strategy as follows. Early defect detection using in-process Pokayoke with the help of sensor-based mechanism. He developed a system with sensor-based mechanism which helps to early identify the faulty products and thereby early detection of quality losses that can reduce further consequences, that is losses related rework and scrap. Employee training program for quality awareness is also one of the mitigation strategy. Recap of initial OE calculation. Scenario was planned operating time 480 minutes per day. Breakdown of losses, planned downtime 60 minutes, performance losses 48 minutes, quality losses 24 minutes lost production time. Initial OE calculation, availability 87.5%, performance 88.6%, quality 93.5%, overall OE 72.5%. Let's see future scenario of OE improvements as seen in previous slides. Planned downtime reduced to 40 minutes due to optimized preventive maintenance schedules of frequently worn out parts, availability of critical spare part during corrective actions, optimization and time required for maintenance when breakdown happens, and modular fixture designed to reduce setup time change over time. Performance loss reduced to 24 minutes by using automated feeding mechanisms, implementing real-time material tracking system, and optimize work allocation and process modification. Quality loss reduced to 12 minutes by early defect detection using sensors and employee training programs for quality awareness. New OE calculation is as follows. Availability coming to 91.7%, performance coming to 94.5%, quality coming to 97.1%, and hence overall OE is multiplication of all coming to 84.1%. Hence, an engineer has identified the losses, conducted the root cause analysis, and provided the solutions through adoption of innovative approaches. Improved result matrix is as follows. Availability improved by plus 4.2%, performance improved by 5.9%, quality improved by 3.6%, overall OE improved by 11.6%. Benefits: increase production output by 11.6%, reduce cost from downtime due to maintenance and defects, enhanced workflows moral due to smoother operations. Conclusion: well, an engineer and the cross-function team has delivered a great efforts. OE improvement is not a single person task. It requires commitment and willingness to work from the production peoples and support from management. Incremental improvements in availability, performance, and quality can significantly enhance OE. Early defect detection and efficient material handling are critical success factors. OE improvement is continuous ongoing process, and since process bottleneck shifts from one station to another, when one of the process is debottlenecked, the next process becomes bottleneck for productivity. Hence, next step will go on, that is implement proposed strategies on a pilot line, monitor results and refine approaches, scale improvements across the organization. Thanks for all. Please feel free to reach out to me for any clarification and provide your valuable feedback.